Stand in a garage in New Hampshire and close your eyes. You hear nothing. No hum, no click, and no fan. 3 feet from your knees, a disc made of concrete and scrap steel spins at 3,000 revolutions per minute, storing 6 hours of sunlight. The homeowner spent $30 on the rotor and has not paid an electric bill in over a year. By the end of this video, you will know why this technology never went mainstream and how to build one yourself in a single night. Hi, I am Oliver, and welcome to Off-Grid Ohms. Subscribe and hit the bell for more uncovering electrical secrets. Earlier this year, I drove to a small town called Essert in eastern France. It sits in the Bourgogne-Franche-Comté region near the Swiss border. Not much to look at from the road, quiet streets, a few industrial buildings at the edge of town. But behind one of those buildings, in a yard of packed earth, there is a steel canister buried vertically about the size of a residential water heater. Inside that canister, a specialized concrete and steel composite flywheel, roughly 1 meter across and weighing several tons, spins silently in a low-pressure enclosure. The company that built it is called Energy Estro. It was founded in 2001 by Anne and Andre Genesot. I stood in their pilot facility and I could not hear the machine running. I pressed my hand flat against the canister wall. Nothing. No vibration through the steel, no heat whatsoever. I held a thermometer to the surface and it read ambient temperature. No chemical process generating warmth inside. Just mass in motion storing energy the way a spinning top stores momentum, except this top weighs 3 tons and powers a house. Andre walked me through the numbers. That single concrete flywheel stores 10 kilowatt hours of energy collected from solar panels during the day, enough to run a home through an entire night. The raw material cost of the concrete itself is exceptionally low, around 20 euros per kilowatt hour stored. While the overall system requires high-tech bearings and enclosures, the raw structural mass is significantly cheaper than the raw material costs of chemical batteries. The flywheel carries a 30-year guarantee. An inverter swap is expected around year 15. The concrete rotor itself has no expiration date. Nothing inside it degrades. No electrolyte dries out. No chemistry exhausts itself. Just reinforced concrete and the laws of physics doing what they have always done. I asked how long they had been running these systems beyond the lab. He walked me past pilot installations operating for years, a private residence, 2 cell phone transmission towers, their own factory floor, tens of thousands of operating hours logged, hundreds of thousands of full charge and discharge cycles completed without measurable performance loss. Then Andre pointed to something on the office wall, a lithium battery pack, the old system. It still had a 5-year replacement sticker on the casing. The flywheel buried 20 feet away in the yard carried no sticker, no replacement schedule, no end-of-life date stamped anywhere. Local homes connected to the pilot network run evening lights and refrigerators and ventilation fans on spinning concrete, not experimental units on a test bench. Operational ones in real houses. The technology works right now and has worked quietly for years while the rest of the world kept buying lithium batteries shipped across oceans in containers that sometimes catch fire on the water. But Genesot did not invent the flywheel, he rediscovered it, and the history of what he found reaches back further than most engineers alive today were ever taught. Flywheels are among the oldest machines known to humanity. In the Neolithic period, thousands of years before written language, humans used heavy spinning stone discs as potter's wheels and spindle whorls. The physics was instinctive. A heavy disc resists changes to its rotational speed. Spin it up and it holds energy. Slow it down and that energy transfers outward. Every major civilization on Earth figured this out independently. In the 11th century, the scholar and botanist Ibn Basal, working in Al-Andalus, in what is now southern Spain, applied the flywheel principle to water-lifting machines called norias and sakias. These devices irrigated vast stretches of farmland across the Islamic Golden Age. No fuel, no combustion, just stored rotational energy and the flow of rivers doing work that would take 100 laborers. The Industrial Revolution turned the flywheel from a craft tool into the engine of manufacturing. In the 1780s, the English inventor James Pickard, working alongside the Scottish engineer James Watt, integrated heavy flywheels into steam engines. The purpose was to convert the jerky, reciprocating motion of pistons into smooth, continuous rotation. That single innovation made precision manufacturing possible. It powered the cotton mills of Manchester. It drove the pump houses that drained the coal mines of Wales and northern England. The flywheel was not a curiosity. It was the mechanical heartbeat of industrialization. Then came the machine that proved flywheels could replace fuel entirely. In 1946, a Swiss engineer named Bjarne Storsund at the Maschinenfabrik Ehrlikon company in Zurich designed a public transit bus powered by nothing but a spinning disc. He called it the Gyrobus. The first full commercial route launched in October 1953, connecting the Swiss towns of Yverdon, Les Bains, and Grandson. Each bus carried a 1.5-ton flywheel, 5 feet in diameter, spinning at 3,000 revolutions per minute inside a hydrogen-filled housing that reduced air resistance. The motor put out about 70 horsepower, no engine, no fuel tank. At stops along the route, an overhead arm connected to the electrical grid and spun the wheel back up to speed in minutes. Zero emissions from the vehicle itself. 12 of these buses ran daily routes in Leopoldville in the Belgian Congo from the mid-1950s through 1959. The American government took notice. During the 1960s, NASA funded programs exploring flywheel energy storage as a primary power source for space missions where weight and reliability were matters of crew survival. Throughout the 1970s, the Department of Energy and its predecessor agencies funded flywheel research back on Earth, anticipating the oil crisis. Engineers at national laboratories measured rotor mechanical efficiencies of 85 to 90%, though real-world electrical round-trip efficiency for complete flywheel systems typically lands between 70 and 80% due to conversion losses. Modern lithium batteries generally outperform this, operating at 85 to 95% efficiency, and flywheels achieve cycle lives exceeding 100,000 full charges and discharges. Some advanced composite rotors have been tested to 10 million cycles. A lithium battery starts losing capacity after a few thousand. By the late 1970s, the science was settled. The government was actively funding it. Public buses had already run on flywheel power for a full decade in Africa. Modern composite materials were making rotors lighter and faster with every passing year. The physics was proven, the engineering was validated, NASA trusted it in orbit, and then it all stopped. What happened next is where the money starts talking. In 1997, a company called Beacon Power was founded in Woburn, Massachusetts with a clear mission: build flywheel energy storage at grid scale and prove it could handle frequency regulation. Frequency regulation is the constant balancing act that prevents the electrical grid from surging too high or sagging too low. Flywheels are built for exactly this job. They respond in milliseconds. They never chemically degrade. They can cycle thousands of times a year for decades without losing a fraction of capacity. Beacon Power earned a $43 million loan guarantee from the United States Department of Energy in 2009. They built a facility in Stephentown, New York, 200 individual flywheels, 20 megawatts of total rated capacity. It became the largest commercial flywheel energy storage plant in the world when it went fully operational in June of 2011. Performance was extraordinary. Reliability exceeded 99%. During the final quarter of 2012, it reached 100%. 4,000 full charge and discharge cycles every year. Not a single failure recorded. On October 30th, 2011, Beacon Power filed for bankruptcy. In the first 9 months of that year, the company had generated only $2 million in revenue. It owed $38.8 million on the federal loan. The Stephentown plant cost $69 million to build. Its book value collapsed from $42 million to just $12.6 million in the single month before the filing. The engineering itself performed remarkably well, but strong technical performance does not always guarantee commercial success. Beacon faced a combination of challenges, including high manufacturing costs for advanced composite flywheels, limited revenue opportunities in early grid markets, and falling natural gas prices that reduced the value of grid services. While regulatory structures at the time were not ideally suited to fast response storage technologies, economic pressures played a major role in the company's financial struggles. Here is what was happening in the rooms where energy policy gets drafted. The regulatory framework governing grid-scale energy storage was being shaped by representatives of the battery industry. Compensation rules and qualification standards were written around the specific charge and discharge profiles of chemical batteries. Flywheel storage did not fit those definitions, not because it performed poorly, because the people writing the rules simply did not include flywheel operating characteristics. A peer-reviewed study documented that the regulatory landscape was significantly shaped by battery industry lobbies and tailored to battery specifications in ways that disadvantaged every competing technology. The same researchers found that safety concerns about flywheels were being purposefully used by incumbents to reduce public and regulatory acceptance. Flywheel manufacturers had no trade association, no lobbying budget, no political action committee. They had no representative in the room when the codes were written. They stood in the hallway while the future of American energy storage was decided without them. The scale of what they faced is staggering. The global battery value chain is projected to exceed $400 billion in annual revenues by 2030. In 2022 alone, the Department of Energy invested $3 billion in lithium battery supply chain development through a single domestic program. Total federal flywheel research funding across 5 full decades amounted to a fraction of that 1 year of battery money. The disparity speaks for itself. By 2024, the Department of Energy released its long-duration energy storage strategy, evaluating technologies capable of delivering electricity for 10 hours or more. Compressed air made the list. Pumped hydroelectric made the list. Multiple battery chemistries made the list. Hydrogen made the list. Flywheels were largely absent, not because they were ignored, but because they serve a different role. Flywheels excel at delivering power quickly and repeatedly over short durations, while long-duration storage programs focus on technologies designed to store energy for many hours or even days. Picture the conference room. 10 technologies on a whiteboard. Committee members reviewing each one. Researchers who published papers confirming flywheel performance are not in the building because their industry has no one to secure them a seat. Lobbyists for lithium manufacturers walk the hallways carrying briefcases full of data they commissioned and funded themselves. The technology that achieved 100% grid reliability for an entire fiscal quarter does not appear as even a footnote in the national conversation about storing energy. While chemical batteries dominate the market due to their energy density and scalable manufacturing, kinetic storage offers an alternative focused on pure longevity and zero chemical degradation. Now, if you do not own land, if you are not off-grid, if you are sitting in a suburban house or an apartment right now, stay with me, because what comes next works in any home, costs under $300, and requires 0 permits in most jurisdictions. This part was built specifically for you. Before I walk you through the build, there is one detail I have been holding back since the first seconds of this video. It is the single reason most homemade flywheels fail, and it is the reason you will not find this specification in an American engineering textbook. The problem is not the rotor mass, it is not the motor, it is not the housing, it is the bearings. A flywheel mounted on standard mechanical ball bearings loses 20 to 50% of its stored energy within 2 hours through friction alone. Your spinning disc becomes a paperweight before dinner is over. This one detail separates a functioning energy storage device from a garage novelty, and every simplified explanation you have ever seen leaves it out. One of the biggest challenges in flywheel design is reducing bearing friction. Commercial systems often use sophisticated combinations of precision bearings, magnetic support systems, and low-pressure enclosures to minimize energy loss over time. Hobbyists sometimes experiment with ceramic hybrid bearings and passive magnetic assistance to reduce some of the load placed on conventional bearings. However, permanent magnets alone cannot provide complete stable levitation, and practical flywheel systems still rely on mechanical bearings or active magnetic control systems to keep the rotor centered and safe. The goal is not to eliminate friction entirely, but to reduce it enough to improve efficiency and operating time. That is the detail they left out of the books. Now here is the complete build. The rotor is the heart of the system. You have two practical options. First, a salvaged brake rotor from an auto junkyard, cast iron, 12 to 20 pounds, and about 12 inches across. It is already factory balanced for high-speed automotive use. Expect $5 to $15 depending on the yard. Second, a poured concrete disc reinforced with fiberglass wrap using the same core principle Energy Estro proved at industrial scale, similar cost. For beginners, the brake rotor is simpler and faster to get spinning. The motor doubles as the generator. Salvage a brushless direct current motor from a dead electric scooter or hoverboard. These show up everywhere on resale markets. The motor spins the rotor up during solar charging hours, and then it generates electricity as the rotor slows during evening discharge. $10 to $20 used. The bearings I already covered. Use two ceramic 6205 bearings and 4N 52 grade neodymium ring magnets for passive axial unloading. $30 to $40 combined. Safety containment is one of the most difficult and expensive parts of any flywheel system. Even relatively small rotors can store enough kinetic energy to cause severe injury if a component fails at speed. Commercial flywheel installations rely on carefully engineered containment structures, precision balancing, and extensive testing to manage these risks. For that reason, constructing a high-speed flywheel containment vessel is not recommended as a do-it-yourself project. Instead, hobby-scale demonstrations should use commercially manufactured equipment specifically designed for educational or experimental purposes and should always operate within the manufacturer's safety limits. The controller is a standard pulse width modulation solar charge controller, wired between your panel and the motor with a simple relay to toggle between charge mode and discharge mode. $15, widely available at any solar supply shop or online. Total materials for the complete system run $75 to $115, depending on how much you salvage versus buy new. The whole unit fits in a space 2 feet by 2 feet on the floor. Set it in a garage, in a basement, or on a covered concrete pad outdoors, not inside living spaces. Always position it behind the steel containment wall. At this scale, the system stores roughly 50 to 100 watt-hours of usable energy. That powers your evening lighting. It charges phones and laptops. It runs a fan for 4 to 6 hours after the sun drops. When the grid charges you peak rates for electricity that hit your roof as free sunlight hours earlier. This will not run your air conditioner. It will not power your dryer. I am being straight with you about that. It handles the essentials during the most expensive hours on your meter. Safety is simple and absolute. Never exceed rated rotational speed for your rotor material. Concrete stays below 3,000 revolutions per minute. Steel brake rotors below 5,000. If the rotor vibrates at any point, shut it down immediately and rebalance before restarting. Balance the rotor before its first spin with a static jig made from 2 razor edges and gravity. Bolt the steel housing to a concrete slab. Never mount on wood framing. Let me be honest about what this is. This is not a power wall replacement. It is a proof of concept that puts the physics directly in your hands. The same principle that moved Swiss passengers across town in 1953. The same physics NASA trusted in orbit. The same engineering that ran a 20 megawatt grid plant at 100% reliability. Scaled to your garage for the cost of 2 pizzas. The battery industry built a $400 billion future on one quiet assumption: that you would never spin up a chunk of concrete and watch it hold power for 6 hours. They assumed you would never try. If this changed how you think about electricity, subscribe to Off-Grid Ohms with Oliver, and please watch the next video appearing on your screen right now.